Hello, my name is Naveen Durvasula, and today I'm going to be talking about how smooth analysis can be used in online auction design. This is work I completed recently in my undergrad at UC Berkeley with Nika Haghtalab and Manolis Zampetakis. Revenue maximizing auctions have been studied extensively in the academic literature and have further found many successful applications across various domains, including internet advertising, spectrum allocation, and real estate. Known revenue optimal mechanisms operate under strong distributional assumptions. Meyerson's auction, for example, requires that the mechanism designer knows the valuation distributions and further that they're independent. But is it possible to do well without them? This is the intent of online learning in auctions. And so in the regime that we study, a single item auction is run every day. Each day, the bidder's valuations are drawn from some distribution that the mechanism designer does not know. Players make their bids, and then the mechanism, perhaps probabilistically, allocates the items to the bidders. Players then make a payment, and the sum of those payments constitutes the revenue of the mechanism. In the online regime, at each time iteration, we pick a mechanism before seeing a valuation profile. And to evaluate how good a given sequence of mechanisms is, we need two things. First, we need to select a benchmark class of mechanisms to compare to. And second, we need to select an adversary, which determines the process by which bids are generated. With those two things, we can define the regret, which gives the gap between the revenue of the best mechanism in hindsight and the revenue of the chosen sequence of mechanisms. One thing to note about this definition of regret is that the supremum lies within the expectation. This means that we don't just want ex ante performance, we're actually asking for good ex post performance on the empirical realized samples. The gold standard here is to have no average regret, which means that asymptotically, the average regret of the revenue of the chosen sequence of mechanisms approaches that of the best mechanism in hindsight. Online auction design has been studied extensively, and the works you see here constitute just a small fraction of the literature. But unlike characterizations of optimal IID auctions like Meyerson's auctions, the results that are in the online auction in the prior free mechanism design literature give learnability results for restricted or parameterized classes of auctions. An example of what I mean by parameterized class of auction is the class of all auctions with individualized reserves, where the parameters there are the reserve prices. And so in our paper, we aim to return to the original promise of online learning in auctions, which is to optimize revenue in a truly unrestricted way without having knowledge of the bidder's distributions. And so the goal here is to say, is it possible to achieve a learnability guarantee relative to the best auction in unrestricted or non-parametric auction class? For example, the class of all incentive compatible auctions. So before we go further, it's worth asking, why is this intuitively hard? And the answer is correlations. It's notoriously difficult to compute optimal auctions, even when the distributions are known when there are correlations. And in our setting, there are correlations everywhere. In our most difficult setting, an unrestricted setting, we consider an adaptive adversary who's able to make arbitrary correlations both across time and between bidders. In the oblivious setting, which is slightly easier, we don't allow correlations across time, but there can still be correlations between bidders. And even in the fully independent setting, which is the easy setting, where every valuation is drawn fully independently, both across time and between bidders, there's still correlation. And again, this goes back to the fact that we require good ex post performance. And so we require good performance on the empirical realization, which is inherently correlated. In addition to correlation, when this is coupled with the precision of an adversary, it becomes clear that things become impossibly difficult. So to illustrate an example of that, consider an auction where there are two bidders and one bidder always bids much higher than the other. An adversary can correlate the joint distribution of the evaluations such that the high bidder's bid is exactly a function of the low bidder's bid. For example, suppose it's this threshold function shown in orange here. And when the high bidder's valuation is a function of low bidders, it's actually possible to have an incentive compatible auction that extracts the full valuation of the highest bidder. And you can do this by making the payment for the high bidder given by the function of the low bidder's payment. And when this occurs, it becomes impossible for an online auction mechanism to optimally learn the auction. The reason is because the adversary can select a sequence of samples in which the online auction mechanism has no idea what the correct threshold is. So suppose, for example, that these data points shown in black are what the adversary sampled. The online auction mechanism would have no way of knowing whether or not the true threshold function is in orange or the one in red or the one in green. And so because of this, the adversary can keep on forcing the auction mechanism to be in this regime where it does not know what the true threshold is. And as a result, it can keep on making our auction mechanism make more and more mistakes. But this example is kind of weird, right? Because it requires this very specific precision, this specific function between the high bidder and low bidder. Is it possible to still capture the general challenge of correlation while removing these brittle worst case scenarios? Well, one idea is to add randomness. So if the adversary couldn't pick these particular data points, but instead they were perturbed slightly by nature, perhaps it's actually possible to do some learning because they can't necessarily construct these functions. So this brings us to the idea of smoothness. Spielman and Teng initially developed the idea of smooth analysis to remove these precision issues from offline learning problems and interpolate between worst and average case. In the modern definition of smoothness, we call a distribution smooth if, for all measurable events, the measure assigned by the probability assigned by the measure is upper bounded by some constant factor times the uniform measure. So in other words, this measure has to be sufficiently anti-concentrated. Haghtalab et al. Extend this to the online setting and remove precision issues from multiple online optimization problems. And we extend their definition here. We say that an adversary is smooth if each of the bidder distributions are smooth, conditioned on past valuations. So to recap, what we want are results for unrestricted classes of auctions. But instead of going straight into those results, we're instead going to start with an example of a non-parametric class, which we call revenue monotone auctions. And the reason we do that is to build intuition for why it's actually possible to learn these auctions, as well as some novel learning theoretic results we show to prove these results that may be of general interest. After that, we'll generalize these results to a much broader family of non-parametric auctions. And finally, we'll return to our original question and see whether or not learning over all unrestricted incentive-compatible auctions is possible. We call an auction revenue monotone if revenue increases with the valuation. And as a consequence of this, the level sets of any revenue monotone auction are monotone sets. That is, if a point lies within the level set, increasing each of its coordinates keeps it within the set. And we exploit a very specific property of monotone sets. That is, if we draw a grid and consider all of the squares that intersect with the boundary of this set, as the discretization gets finer and finer, the Lebesgue measure of these boundary squares gets smaller and smaller. And so what this means is that actually a smooth adversary can't target the boundary. And why is this intuitively helpful? Well, the boundary intuitively is the place where we're unsure of what the revenue is. The interior, we have a solid understanding of what the revenue is. And so if the adversary can't target the boundary, perhaps learnability is possible. So what's our actual no-regret mechanism for monotone auctions? Well, our general strategy is to find a small cover for the benchmark class, such that the best auction in the small cover has similar performance to the best auction in the benchmark class. Once we find this cover, we can run hedge or any other standard no-regret algorithm for finite options to get a no-regret mechanism. So to find this cover, we actually do this in 2 steps. And in the first step, we're going to swap the expectation of the supremum. And why do we do this? Well, in the first case, where the supremum is inside, we're dealing with these sequences of empirical samples. And this is a much more unstructured object to work with than theoretical distributions, especially for end goals to find a net. And the way that we actually show that you can swap these 2 things and the value remains similar is by proving a novel learning theoretic result. We show that the empirical measures from smooth sequences of distributions agree with the true measure on all monotone sets concurrently. And the intuition for why this holds goes back to that fact I mentioned earlier about monotone sets. Tools from VC theory, or standard tools from learning theoretical literature, already show that for nice sets, for example, unions of boxes, the empirical measure will converge to the true measure. What we do here is we actually extend those results to all monotone sets when the distribution is smooth, because what we can do is we can look at the boundary, and the boundary by that fact I mentioned earlier has small Lebesgue measure, and so the smooth sequences of distributions will have small measure on that boundary. And then by VC theory, we have agreement on the interior, and so putting those 2 things together, we get the desired result. Next, we actually have to find the cover. And to do that, we're actually going to first build a cover over distributions instead of going straight to a cover over mechanisms. And we're going to build a cover over distributions such that the worst case error on monotone sets is small. And the intuition for why such a cover exists, again, is similar to the previous result. In essence, we can construct a net of distributions where on all unions of boxes, there's small error. And then because the boundary has small Lebesgue measure, by smoothness, we can discount it. Once we have our net of distributions, we can get a net of mechanisms by considering all optimal mechanisms for net distributions. And because any net distribution has small worst case error on monotone sets, and all the level sets of the revenue function are monotone, this small cover has the property where there exists some element of it with revenue that's close to the best mechanism in the original benchmark class. So now that we've shown why learnability is possible for the non-parametric class of revenue monotone auctions, we extend this result to a much broader family of auctions, which we call smooth auctions. So the key observation to make here is that for the entire argument for the monotone auctions to pass through, the only property that we needed is that the boundary of the revenue level sets shrank as the discretization, the grid discretization became finer and finer. And so we defined smooth auctions to be auctions that satisfy that exact property. And this class of auctions is very, very large. For example, the class of all competitive monotone auctions, which we define as all auctions where the allocation weekly increases with the bidder's bid, but also weekly decreases as the opponent's bids increase. That class of auctions already cannot be tractably handled by standing learning theoretic tools, such as scale-sensitive EC dimension or pseudo-dimension. However, it is a smooth class of auctions and can be dealt with tractably by the learning theoretic results that we described earlier. So now to our main results, we show that when both the adversary and the auction is smooth, no regret learning is indeed possible. And so we prove this for the oblivious case, and we further generalize this to the adaptive case when we consider deterministic auctions. But is it possible to go all the way and learn over all unrestricted incentive-compatible auctions? Well, as hinted at by the initial example with the high and low bidder, this is indeed not possible. So we also show corresponding lower bound results that show that smoothness of the auctions and valuations are both necessary for learnability. But upper and lower bounds aside, the main takeaway here is that we can talk about online learnability for a much broader class of auctions that are specified by axioms or rules as opposed to parameters. So contrast, for example, the description of competitive monotone auctions, which was given by a rule on the allocation function, as opposed to, for example, the class of all auctions with individualized reserves, which are specified by the parameters, which are the individual reserves. So the ability to learn these classes motivates further study of non-parametric auctions. And we further posit that smoothness in particular is a good sweet spot between learnability and richness. We conclude with some open directions. One main open direction, actually, is to see whether or not there are large families of distributions for which the revenue optimal auction is already smooth. So, for example, in the independent case, Meyerson's auction is already a smooth auction. And so we already have that the tools that we've described here would indeed find the true revenue optimal auction in the unrestricted case when the distributions are independent. But say that you then have a distribution that doesn't fall in this category. This leads us to our second open direction. If a distribution doesn't have an optimal auction that is smooth, what's the approximation power of smooth auctions? Does there necessarily exist a smooth auction where the revenue of that auction is close to the optimal auction of the original distribution? Finally, we confess that we did not optimize either the computational efficiency of our methods or the dependence of our bounds on all parameters. And so it would be a worthwhile cause to see how tight those are, especially for our learning theoretic results, if those can be improved. Thank you.